In this video, I will graph the two-phase envelope on top of the isotherms from part 3 using the Maxwell construction. So how we're going to do this is we are going to find the pressure at which this area under our pressure line and the area above our pressure line are both equal. So we'll do this by creating a function that finds the areas, then a function that calculates the difference between the two areas, which we'll then use root solver on to get the roots. And then from there, we will be able to graph the corresponding pressures and the liquid volume and the vapor volume to get our two-phase envelope. So we need to start by getting the areas. I will create a function called areas, and how we are going to solve we'll pass temperature and pressure to this, and how we are going to get the areas is we'll be using a SciPy function called quad, right? It's based off a method called of Gaussian quadrature, which is a way of finding area under the curve, and it's actually quite accurate. So here is the import statement that I'll be using. So from scipy.integrate, import quad, and then how this function works is it takes an integrand and a lower bounds and an upper bounds, and it'll return the area, right? So we need to define our integrand. We'll pass the specific volume to it, and our integrand will be just the pressure we are trying to determine minus the pressure that we find from our equation of state, which is just this function that we created earlier, right? So now that we have our integrand, we can return the two areas. So our first area will be quad of our function, which is the integrand, our first root to our second root, right? Our first root will be here, and it'll give the equation and the area, or it'll be the area all the way to here, right? And then we'll also return our second area, which will be our second root to our third root. So the integrand, and then will be our second root to our third root. Now, we need to calculate our roots. So we already have a function to do that, and it's this SRK sub V. So this will calculate our specific volume roots for that given temperature and pressure. So T, comma V, and we'll have V1, comma V2, comma V3 will equal this. So now we have our function to get the areas. So let's see if this works. I'll plug in a temperature of 500 and a pressure of 10,000. And there we go. But you see it returns 4 numbers. So this is our first area. This is our second area. Notice how one is positive and one is negative. So when we add them together later, we can set them equal to 0 and find that root. And that will give us the vapor pressure. But right now, we're getting 2 separate numbers. So this first number is our area, and the second number is the error. And we don't need the error, so to get only the area, we need to get the first value in each array, right? So now if we run it again, we get, I need to do it to both of them. So for our left side and our right side, so now we just get the 2 areas. So from here, we can use this area function and create a function which I'm going to call area differences. And we will pass a vector of our unknowns and the temperature. right? Because this is the function that will pass to our root solver. And the way the root solver is set up is it's set up to solve multiple equations with multiple unknowns. So it takes a vector of unknowns as a parameter that passes to it. So we need to put in a vector, and in our vector of unknowns, we just have pressure. So we'll pull that out of the vector, or out of the array, right? We're passing an array, and we'll pull our pressure out of the array, and then we can calculate our left and right areas, which I'll just call left and right, and we'll use our areas function. And then what we need to return is the left plus the right. Because as you saw before, the left side was positive, the right side returned a negative value, so when you add these two together and they're equal, it'll return 0. So now let's use root and go ahead and get the vapor pressure for a certain temperature. So we will put in our function, which is area diff. We will put in our guess, which has to be in an array. We'll guess 10,000. And then we also need to supply additional arguments, right? Because we have t, which is held constant when this root solver goes through and iterates. So we indicate this by args equal, and then we'll set it equal to the temperature. So we'll just run through for 370 degrees. And we'll go ahead and run that. There we go. So this is our solution. It's about 80,000 pascals. And we just need that number. So to get that, we need the x attribute, right? And it's returned as an array. So we just need the first value of that array. So now if we run it again, we only get the pressure value. So this value is the vapor pressure at a temperature of 370. So now I'm going to create a for loop to collect lots of vapor pressures and get their corresponding liquid volumes and gas volume, and we'll use that to plot. So actually, before we create the for loop, I'm going to quickly get the 3 roots at that temperature. So it'll be VL, we'll have a V intermediate, which is that intermediate root. I'll just call it V inter, and we'll have V or gas volume. And we'll get these using the SRK equation of state for a specific volume function that we wrote, and we pass temperature and pressure to it. So I'm going to go ahead and set the temperature equal to 370, and then I'm going to change this argument here just to represent temperature. It'll be a little easier when we create the loop later. So now we have our roots, which is the liquid volume and the gas volume, and we also have our vapor pressure. So now if we create groups of these and calculate a lot of them, we'll be able to graph or plot our two-phase envelope. So let's use the for loop. We'll go through temperatures. We'll start at 275. We'll go up to 600, and we'll have 100 steps. So then we can get rid of this temperature up at the top and indent these to be in our loop. So now every time we run through the for loop, we need to store our values. So let's create lists to store each value. So we'll have one pressure list, which will store the vapor pressures. We'll have one list called the liquid volume list, which will store our liquid volumes. And then we'll have the gas volume list, which will store the gas volumes. So now we need to store these values, so we'll just append them to the list at the end of each loop once they're calculated. So we'll append the pressure, and then I will append the liquid volume, and then I'll also append the gas volume to its corresponding list. And so now, right now, how the loop is set up, we are running through with the same guess each time. So instead of doing that, I'm going to use the calculated value. We'll start with a single guess. We'll just start at 100. And then each time it calculates the vapor pressure, we'll store that for our next guess. The reason why I'm doing this is because each time let's say we calculate the vapor pressure for 275, it will be the closest value that we know to the vapor pressure at 280. And then same thing, we'll calculate 280. For 285, our best guess will be what we calculated just before. So I'll put our guess equals each vapor pressure at the end of our loop. So now we are able to go ahead and graph it. Let's run this. Doesn't quite like my function here. Oh, it's because we didn't change guess. Here we go. That wasn't the error. So I found my error. All it was instead of pressure, we need to pass the vapor pressure to our function. So now it'll calculate all the temperatures and we'll be able to graph it. So I'm going to go up and grab our graph from part 3 and copy it down into our code down here. There we go. So now I'm going to change this to figure 2. Since this is our second figure in our code, that way we won't mix it up with the one above. And I'll go ahead and add in a scatter plot to graph our two-phase envelope, and we'll see how it looks. So we'll use add scatter. Our X will we'll first graph our liquid volume, then we will graph our vapor or our pressures for Y, and then we'll go through and copy and paste this line again, and we'll do it for our gas volumes. So Y equals plist, we'll do our mode. The mode will be lines, so it graphs as a nice line, and we'll change the color to white, so it's really easy to see. So let's go ahead and graph that. And you can see it start. It's coming from this side. So there is our first set of liquid volumes. So now I'm going to go ahead and graph the gas volumes. And you can see it start to come from the other side, right? Eventually we want this to look like a nice envelope. And we're not quite there. So right now it looks like we need to go up towards higher temperatures. See, it's getting there, they're almost connecting, but not quite. So let's see if we raise our temperature just a little bit, if that helps. Now the highest that we can go is the critical temperature, and if you see, if I put in a value above the critical temperature, we'll get an error in our code. Because we're passing the critical temperature and it runs into an issue in our root solver. So I will put in 620. We'll see if that's high enough, but not too high. And go ahead and I'll run this again and we'll see if it's better. So we're still not quite there, right? They're not connected. So what I'm going to try next is I'm going to try to combine these into one list, and we'll see if that solves the issue. So if I combine the liquid and gas volumes into one list, that way we're graphing one continuous curve. Hopefully we'll get a nice smooth curve. So how I'm going to do this is I'll create a list of the pressures for plotting purposes, which will just be our list of pressures. And then I will create a volume list for plotting, which will combine our liquid volumes and will append the gas volumes. But right now, how the gas volumes are being calculated, they're being calculated from right to left, right? You see down here, we start on this way and we're going up left, where these, the liquid volumes, are starting from the left and going to the right. So we need to flip our gas volumes around in the list so that it graphs as one continuous curve. So instead of starting from down here, we'll flip it so the values start up here. That way we have one nice smooth curve. So to do that, we'll come back up here and we'll append the list, but we'll go from the start to the end and we'll increment by -1. So this will start from the end of the list and go to the beginning. So because we did that to our volumes, we need to do the same thing to our pressure plot. Otherwise, we won't have enough points for pressure to graph all the volumes. So I'll do plist and do the same thing. We'll append the start, the end, and we'll go opposite. And I'll go ahead and run that. And now we can come down here, and instead of plotting both of these, I just need to plot one, and X will be our vplot variable, and Y will be our pplot. And let's go ahead and see if this solved our issue. Kind of. So they're connected now, but it's not quite the nice smooth top that we want. So our biggest issue right now is we don't have enough points close towards the critical temperature, right? Because as we get closer, we're going to want to plot closer and closer and closer to the critical point. When you're way down here, it doesn't matter as much how far how close your points are together. But as you get really close to the critical temperature, you need a lot of points close together to get a nice smooth envelope. So how we're going to do this is we are going to plot T as a function of e to the -x. So if we plot e to the -x, we get a function that looks like this, right? So as we come down and as you get closer to 0, the points will get closer and closer and closer together, right? So now what we need is we need the opposite. So as we get closer to the temperature, right, as we get higher towards the critical temperature, we need closer points. So let's flip the function. And we need to translate it up 1, so it starts at 0. So we add 1. Now we need to scale the function so it starts and ends where we want it to. We need it to end to the critical temperature. So we're going to multiply it by the critical temperature of water, which is about 647, minus our starting point, which I'm going to start at 275. That way, since we scaled our function up to 0, we can see that up here, it goes all the way up to about, not quite to 600, because we needed to translate it up, right? So then we'll translate it up, so that way it goes all the way up to our critical temperature of 640. So we'll add the initial temperature. Now, when we come to the top, it has what we want. So as we get closer to the critical temperature, our points get closer and closer and closer together. So now we're going to go and change our code to reflect this. So instead of linearly calculating t, we're going to put in a dummy variable, and we'll just go from 0 to, we'll go to up to 7, and we'll have 500 points in. That way we have a lot of points, and it'll give us a nice smooth curve. So now we need to calculate t, right? It's that equation that I just showed you. So it'll be the critical temperature minus our starting temperature of 275 times 1 minus E, which is, in this case, we'll use numpy.exp of negative x, which is e to the negative x, plus 275. And I'll double check my parentheses all match up. We'll go ahead and run that. And now let's try graphing. And there we have it. There we have a nice smooth two-phase envelope on top of the isotherms.